All right, so welcome everyone to the weekly Space Hangout, the Science Hangout here on Cosmoquest. I'm Emily Lakdawalla from the Planetary Society, and with me is Robbie Herrick of the University of Fairbanks, Alaska, who I know is a Venus geologist, but apparently he's worked on lots of other planets as well. He's got some really fantastic new data from a planet that we have not sent a geology mission to for a very long time. Before I start asking him some questions about the work he's been doing recently, I would like to ask all of those of you who are watching this to please go to Google Plus and +1 it. Let us know that you're there. Post a comment, ask a question. I'll get to some questions later on in the broadcast. You can also ask questions via Twitter using the hashtags #CQX, #Hangout. And now I think we'll go ahead and get started. So, Robbie, you have been working on a mission that is near and dear to my heart. I worked as a graduate student on Magellan, which was a mission that orbited Venus for many years and took these absolutely stunning radar images of nearly the whole planet. And people who are watching space exploration now have seen radar images most recently from the Cassini mission to Titan. But to me, they always hark back to the Magellan mission's incredible data set. And you, I guess, have been doing some work recently that has created basically a brand new data set out of from a mission that ended almost 20 years ago now. So I was wondering if you could tell us a little bit about that.
Sure. So, of course, when the Magellan mission was going on, that was quite a long time ago. The capabilities of computers at the time were a lot less than they are now. And so just to put it into context, when the Magellan mission was going on, the World Wide Web had not been created yet. Magellan was the first NASA mission where the data was distributed electronically, and at the time it was distributed electronically by compact disc. So people on the team were mailed boxes of compact discs, and that's how you got the data. And all the data was it was so much data at the time that only about 10% of it was sent around at full resolution, and most of it was sent at a lower resolution. And you got these compact discs, and all the data was divided into 1 megabyte tiles because computers at the time could only handle a 1 megabyte image at the time. And
and I just have to interrupt here because that was one of my first impressions of being a student, was walking into the lab at Brown, and they had these big cases that had photographic prints, and then there was an entire wall lined with just mountains of CDs from the Magellan mission. And I spent an awful lot of my time as a student, especially as a first-year student, looking up the index, trying to figure out which image was on which CD, and taking each of those 1 megabyte squares, which were all separate files on the CDs, and assembling them into a rectangular image that was a whopping 8,000 pixels wide. Who could handle that at the time? It was pretty crazy.
Yeah, and so at the time, during the Magellan mission, the way that Venus operates, it rotates very slowly in a retrograde manner. And so because it rotates so slowly, the way the mission operated was to simply orbit the planet in a polar orbit and gradually build up an image of the whole planet. And so after a Venusian day, which is 243 Earth days, you had a map of the whole planet. And at the time, the Magellan mission imaged for 3 Venusian days. And on the 3rd Venusian day, it imaged using the radar at a different look direction than the first Venusian day. And the result of this, I won't get into how a synthetic aperture radar works, but the end result is that you end up with a pair of images that are very much like a stereo pair of photographic images.
Yeah, it's most of the time when we have these polar orbiters, and actually the spacecraft that are imaging Mars and the Moon right now at very high resolution, typically they're in a polar orbit and they look straight down most of the time. They have a nadir view on, that's N-A-D-I-R, nadir, looking down at the planet. And then if they want stereo coverage on the next orbit or on an orbit maybe a few times later, they'll look at a slightly different angle at the same spot. And having the two slightly different angle looks gives them a bit of parallax from which they can get topography. Magellan worked somewhat similarly, except that it never looked straight down to get images. It was always tilted off to one side, and then the second look was tilted a little bit more so that you had some parallax from which you could assemble topography.
Right, and so yeah, the processing of radar is somewhat different than the processing of photographic images, but for the purposes of this discussion, it's very similar, the end result, and the effect is the reason you get a 3D effect. It's as if you are looking at something with your eyes separated by many kilometers instead of just a couple of inches, and so if you have that data, then you can use some relatively simple trigonometry and translate the movement of features due to parallax in the two images and change that into relative elevations. So this data was collected back in the early 1990s, and the problem was that the data set at the time, each day's worth of data is a few hundred gigabytes, and that was considered an enormous amount of data to handle to do this stereo processing with. So it simply didn't get done, and there were some tools developed that allowed one to use very small amounts of stereo data and do some processing on small areas, and it was somewhat labor intensive. And so what we did was go back and now, of course, with modern day computers, a few hundred gigabytes of data is a little bit more than fits on an iPod, but not that much. And so it's a fairly small amount of data to handle. And there's some more sophisticated software out there that allows you to automate a lot of the data processing, and that's what we did. And so we went back and reprocessed this stereo data to generate topography. And the reason that was interesting at the time during the Magellan mission, in addition to having an imager, the radar was used as an altimeter and looked straight down and measured the time for the radar pulse to go down and back. And as an altimeter, the Magellan mission collected data that had a horizontal resolution of about 20 kilometers, 10 to 20 kilometers. With the stereo data, we're able to, for the part of the planet that has stereo coverage, we're able to improve upon the horizontal resolution and get down to about a kilometer or two horizontal resolution. So, so it allows you to see some of the details of the topography for the areas that were imaged well, and we didn't really know what the topography was.
So I'm sharing right now an image that you sent me actually from a presentation showing off your new data set. And on the left over here where it says GTDR, GTDR stands for Gridded Topographic Data Record. And it's the map that they made from the altimetry data, which was, as you can see, at a much, much lower resolution than the beautiful images that we got back from Magellan. And then on the right, I can see your new topographic map. So tell us about this a little bit.
Okay, so what you're looking at, this was just an example to sort of show off the topography. And right down the middle of this particular area is on the side of a large plateau area on Venus called Avda. And in the topography data, the highs are the orangish and the lows are the greens. And what you can see is that in the new data on the right, you're able to make out some of the features of the lava tube that is going through the middle of the radar image that's in the middle of the screen there. And you can see the initial collapse feature where the lava was initially coming out. And so you're right, this is right at this demonstrates about the capability of the new data set. And the reason that getting this level of detail is important is that it allows you to start modeling and understanding some of the physical processes that form these features, and in doing so you can learn something about the depth and the width versus the width of these channels has something to do with the temperature of the lavas and how they're flowing across the surface and cooling while they flow and things like that. So the new topography allows you to do some quantitative studies of geology that you couldn't do before. It also helps to distinguish to identify features that some features are obvious in the topography and not so obvious in the images and vice versa.
Yeah, and I think those images also show off some of the things that I think are just so wonderful about the Magellan images. And by the way, is my face moving on the video? Because it's not on my own screen. Oh, there it goes. Sorry, Google Plus is still beta, so you never know what it's going to look like. Venus is just covered with these absolutely amazing volcanic features, and it took me actually a long time of looking at Magellan images to just get into my head how much volcanism we're talking about here. Everywhere you look on the planet, everywhere, there are little tiny shield volcanoes. There are these canals and tubes that lava must once have flowed through. You can see lava flows of all kinds. It's really, I mean, have you ever imagined, standing on it or trying to, what life would be like underneath the clouds on Venus on a planet that had so much volcanism?
Well, I think it would be the most, well, to me, the most interesting thing that you would notice if you were standing on most of the surface is how flat it is to begin with. You would be on volcanic lava plains, and the planet as a whole is extremely flat. About 80% of the planet is within 500 meters of the mean elevation of the planet. So so as you walk around the planet, it's remarkably flat. If you look at there are some huge volcanoes in terms of their width. There are volcanoes that are 1,000 miles across, so they would, cover the entire state of Arizona. And they're as wide as, say, Olympus Mons on Mars, but they're very flat. So you would have, unlike Olympus Mons, which is over 20 kilometers high, the volcanoes on Venus are only 3 or 4 kilometers high while being the same width. So you'd have these very low slopes that you could walk across, and unfortunately we don't have enough resolution to know exactly at sort of the human scale how rugged the topography would be, other than we have a couple. There's a handful of landers that the Soviets landed on the surface, and from their view, it looks pretty flat, like something that you would have no problem walking around on. But there are other areas of the planet where we just don't know. We get some clues from Magellan data, but we just don't know at a human scale of walking around really what it would be like. We don't have nearly the same detail that we get from, say, the Mars rovers and the Viking lander and then the high resolution cameras that we have for Mars. So yeah, so this is...
I just had to share here these. This is one example of one of the images. This is Venera 14, and you can see the platy lavas that it landed on. These landers had some funky cameras that they were looking down very close to the lander at the center of these panoramic images, and they swept up toward the edges so that they just barely nicked the horizon in the corners here. So you're mostly seeing rocks in the foreground, but it's this kind of platy pahoehoe lava that you might see on the slope of a Hawaiian volcano, and an awful lot of Venus must look like this.
That's the best guess as far as we can tell. Yes, that's right. I mean, at the resolution of Magellan, we see a very large portion of the planet that seems to resemble lava plains like you might get at around the Hawaiian volcanoes. There's other places around the world like maybe the craters in the moon area in Idaho is probably a good. I think it's in Idaho. Yeah, that's a good example. And so it would be an interesting. The most interesting thing, though, about Venus is that because of the way the atmosphere operates near the ground, it's very dense and there's very little wind. So when you're walking around on Venus, of course, there's no vegetation, but there's also no erosion, and so you would be, the only analogs on Earth are places that are very recent and have experienced no erosion. So there's very little sand, and so it really is just places like around the new parts of the big island of Hawaii and other places where you've had lavas that have poured out within the last several thousand, tens of thousands of years on the Earth.
Yeah, the way the atmosphere modifies craters on Venus is really fascinating. So I've got an example of one here whose name I forget. I don't know, as a quiz for you as a researcher, maybe I should ask you to name it off the top of your head.
I cannot name it off the top of my head. I could probably figure it out in a few minutes if I...
So this is a Venus impact crater.
I do know it's on the side of a corona there. It's... yeah, so what would you like to... It is the appearance is unusual. Would you like me to?
Yeah, talk to us about why craters on Venus. They're very beautiful, but they're very strange looking. Okay.
Well, the first thing, first let me point out one of the differences between radar image and an optical image. So the radar image is sensitive to this particular one operated at 12 centimeters, and so it's sensitive to features at the sort of 12 centimeter scale. And when you look at this image, the ejecta surrounding the central crater is very bright because it is rough at the scale of 10 to 15 centimeters. And so so if you were to look at this in an optical, with a photograph, it would have a different appearance. The ejecta is probably more or less the same rocks as the surrounding. So the color, if you were to look at it with your eyes, the color would be very similar. But here the ejecta shows up as very bright because it's very rough, it's very blocky from all the material that is thrown out. Now, this is also different from what you would see at the moon because you can see that the edges there look kind of digitate and like there has been some flow in the ejecta rather than, say, on an airless body like the moon where the ejecta just kind of gets thrown out and you get a gradual thinning of the blanket as you go away from the crater. Here, what we think happened, and we only have a vague idea at this scale of what happened, but what we think happened is that the material that was thrown out of the crater mixes with a very dense, turbulent atmosphere of Venus and then things flow away from the crater, sort of like a pyroclastic flow around some of the volcanoes on Earth. So stuff mixes together, and you get a density current, and it flows out away from the crater, much like on a volcano.
I'm throwing a slightly different crater at you now. Just this is a more famous one, I think, because when you zoom out from this one, you get to another one of the weird things about Venus craters.
Right, and so this now, if you look at this crater and you go even farther out, you can see right around the crater is that rough, very bright digitated ejecta blanket, and then outside of that you can see a bright area, and then right towards the edges of the image you're looking at, you get kind of a west or a left-facing parabola. And all of this, all of these very distal features have to do, we think, with the interaction of ejecta as we get, as the ejecta gets, some of the ejecta, particularly finer material, gets thrown up into the very uppermost parts of the Venusian atmosphere. And when that happens, you have some fine material, and then once you get about, I think it's about 40 or so kilometers up in the Venusian atmosphere, you have very strong prevailing westward blowing winds. And so material, if you have a big enough crater, the act of ejecting material kind of punches a hole through the atmosphere, or through part of the atmosphere. You throw some material up into the upper atmosphere, and then it gets blown westward and creates this parabola out west. We don't understand all of the details of this process, because some of the parabolas are dark, some of them are light, some of them show up in the imaging quite well, some of them only show up in a slightly different data set called the emissivity data set. So we don't understand the full process, but it's the general idea is stuff gets thrown up into the upper atmosphere, and then prevailing west winds make this large parabola associated with what seems to be only the freshest craters. And there's eventually these parabolas seem to go away with time, and how they get erased with time is another story. It's presumably some combination of weathering and a little bit of wind blowing things around, and so on.
So actually, before I ask you the next question, I should pause for station identification. Again, this is Emily Lakdawala of the Planetary Society on the weekly science hangout on Cosmoquest, and my guest is Robbie Herrick of the University of Alaska Fairbanks, who's talking with us about Venus topography and features on other planets as well. In about 10 minutes or so, I'll probably start throwing this out to questions from the audience. You can post questions in the comments on Google+, or on Twitter by posting a question with the hashtags #CQX #Hangout. And I'll deliver them to Robbie and put him on the spot. But in the meantime, I wanted to ask you, Robbie, to talk a little bit more about maybe some of the surprises you've learned from your newly processed Venus topography data set.
We've just sort of gotten into using the new topography to do things. I guess a couple of scientists I've been working with have been, there's one group that's up at Wesleyan University that has been using the data to better quantify the folding of the topography that is in the what are known as the tessera regions on Venus. And Venus is unique among the other terrestrial planets in that it's the only one besides Earth that has what you would consider true mountain ranges that result from something happening where you have crust on the surface moving horizontally and crunching together and making a mountain range like the Rocky Mountains or the Himalayas. And so,
you know what's exciting, Robbie, is that at LPSC this week, the messenger team showed evidence for fold thrust belts on Mercury, where huge, long, linear chains of these folds that clearly do crustal shortening. They've mapped them across some large areas of the planet. So that was pretty exciting. That added another planet to that very short list.
Yes, I should update that statement to yes. The on Mercury I think they're still going with the main cause of that being a general shrinking of Mercury, but there's also some evidence now on Mercury that it does have some sort of true tectonics where convection in the planet's interior is having an effect in dragging things around on the surface. So, however, I would still say that what's going on Mercury is, I think, still not nearly as Earth-like as what happens on Venus. On Venus, there are some areas that are where you really have some true fold and thrust belts, and you have also some areas that are very extensive, very wide, hundreds to a few thousand kilometers wide, that are intensely folded. And one idea is maybe these are things that are like Earth's continents, but just not eroded at all. And there's some speculation. We don't know whether they are of a different composition than the rest of the planet, like Earth's continents. But so one of the things that my colleagues have been doing is trying to figure out from what you can see whether the crunching that you see represents a whole lot of shortening of crust or just a little bit. And they're looking at sort of the amplitude of the folding and how symmetric the folding is, and they're coming to the conclusion that it looks intensely deformed, but you're only shortening things by maybe 1% or 2% to generate that. Another thing that we're doing with the data is looking at some of there's a few areas where we have coverage in the stereo of some of the really large volcanoes. So that's an example where these are two examples of the deformed terrain that you put up on the screen. And so the images are in the black and white and the topography is in the color. And then on the bottom is an exaggerated profile through the topography. And so we're using that to kind of measure, try and estimate the amount of actual crunching of the surface that you need to produce the rugged topography that you see. And so as I was going to go on, the other thing that some colleagues at the Lunar and Planetary Institute in Houston are working on is looking at some of the large volcanoes. Some of these large volcanoes on Venus have rifts going through them. And what you can see in the inset of this photo is the topography from just the altimetry data, and the larger image is the topography from the stereo. And what's interesting about this is that in the stereo-derived topography, the rift that goes through this volcano is much deeper. And so this changes the understanding of the timing of the rift relative to the volcano. And what we had before, we thought that the rift, and as we could see it, was forming sort of simultaneously with a lot of the volcanic flows that were coming out in the volcano. Now that the rift is so deep, it says that a lot of the strain and a lot of the rifting occurred after the volcano was almost entirely formed, and then the rift forms and cuts quite deep into the volcano. And so we're starting to be able to use this to try and get an overall picture of how the volcanoes are related to the rifts and the timing, and then that translates into a broader story of how those things relate to what's going on in the interior of the planet, which ultimately is causing the rifting and the big volcano. So.
And this kind of thing, I think, it's what makes Venus so fun for structural geologists, because there are so many different events that happened, and they all overprint each other. So you've got the law of superposition happening everywhere. You've got rifts, you've got volcanoes, you've got flows going into things, you've got craters getting deformed, and it's all on top of each other, and yet none of it has been eroded by not even wind, because the atmosphere is so thick that wind erosion doesn't seem to play a real strong role on Venus, even as much as it does on Titan, which has those dunes blowing around. It's all laid bare for you to see, and even though it's laid bare for you to see, it's still kind of really difficult to figure out, and it's been the source of much debate since Magellan first arrived.
Right, yes. Well, part of that is that while Magellan gives you a great regional picture of the geology, and you can see, if you look at, say, some of these large volcanoes, you can see some of the more gigantic flows. Magellan, in general, does not have the resolution for you to be able to see individual volcanic flows in most cases, and it doesn't have the resolution for you to see individual faults that help you, really figure out exactly what's going on in terms of the history of things. And so the end result of this is that this has resulted in some completely different worldviews about the overall global geologic history based on the way that people have made their inferences beyond the actual resolution of the data, and what they think, based on what I see at Magellan resolution, what I really think is going on at resolutions that you just can't resolve. So
sounds like we could use another mission to Venus.
Well, yes, of course, and I would like to. It's been so we're going on 23 years since NASA last launched a mission to Venus. So it's been a long time since there's the Europeans have a mission that's orbiting Venus right now called Venus Express, but its main focus is studying the atmosphere of Venus and trying to understand mostly the circulation of the upper cloud deck, and using some instruments to get some of the composition of different layers in the upper atmosphere. And there's been some of that data that's been useful for studying the surface, but not much. And so
the funny thing about Venus Express is that, like Cassini at Titan, it does have a camera that is capable of seeing what are called seeing through windows in the atmosphere, a region where the primary opaque constituent of Venus's atmosphere is somewhat transparent to light. So it's an infrared wavelength. You can sort of see through the clouds, but the problem is that at any kind of infrared wavelength at Venus is so hot that it actually radiates heat at those wavelengths. And as on Earth, things are colder at higher elevations and hotter at lower elevations. So pretty much all you can see when you see with infrared light through Venus's clouds is topography. And it's really hard to take that effect out and see any kind of detail using these optical imagers. So we really got to get something beneath the clouds.
That's right, and I'm a fan of. I would like to see us go back. My general feeling is, based on what happened in the 1990s. After after the Viking mission, we had a data set for Mars from Viking that is pretty much, in many ways, similar in quality to the data set that we now have from the Magellan mission. And of course, in the late 1990s, the Mars Global Surveyor mission flew that had the Mars laser altimeter, MOLA. That was the Mars Orbiter laser altimeter. It was originally Mars Observer, of course, until Mars Observer failed. But so the MOLA data, and then the Mars orbiting camera, which was the MOC data, and those two instruments, which provided higher resolution of data on the topography and imaging of Mars, completely revolutionized our understanding of Mars and showed, really showed the history of Mars to be a lot more complex and interesting than we got from the Viking data. And with that data, we could, there were a lot of things in Viking that were assumed to be single geologic units that turned out to be incredibly complicated units that had occurred over long time spans. And so I expect that if we did something similar at Venus, we would get a completely revolutionary understanding of the history of Venus. And so, to me, what we need for Venus is what was provided by MOLA and MOC at Mars. And of course, the subsequent imaging systems that flew on later orbiters like Themis and the HiRISE camera have only reinforced that belief that there are other things, of course, that you can do at Venus. There's a whole list of interesting missions you can do, but for my personal bias, in terms of bang for the buck and what you can, it's hard in terms of our studies of Mars. It's hard to beat the MOLA and MOC instruments in terms of how they revolutionize the understanding of Mars. And I think, those are good things. That's what I would fly at Venus if I was to go next. But
you're the one on camera, so you can be as biased as you want.
Okay.
With MOLA and later on, we've actually we've flown Lola at the Moon, and now it's MLA at Mercury on Messenger. That's provided us with these new insights into the fact that there are fold thrust belts and possibly maybe even some kind of small mantle convection features on Mercury. And so yeah, laser altimetry is really fantastic. But can you do laser altimetry at Venus? Can you get an optical laser? Do you need a different kind of wavelength of laser in order to get through those clouds?
Right. So at Venus, no, you cannot use a laser altimeter. And what you would have to do is there are various schemes that you use with radar to improve to get high resolution topography. There's actually three different ways that you can get topography at Venus using radar. One is simply to use a more sophisticated radar altimeter than was done with Magellan, and you can get a somewhat narrower footprint, and you can do some more sophisticated processing, particularly if you have more power going into your altimeter. You can do some more sophisticated processing, and you can get something pretty good that way. Of course, as we demonstrated, you can use stereo imaging if you were to, if you do higher resolution imaging of the surface of Venus. and you do it in stereo, then you can get topography that way. And then the third option is using a technique called interferometric synthetic aperture radar, and this is a little difficult to explain in a very short time frame, but the general idea is that you take images that are from a platform that are separated by fairly short distances, and you take an image and then take another one from tens of meters different perspective, and it's you use the interference pattern of the individual wavelets that are coming back and the distortion of that pattern. You get a particular pattern, and then topography distorts that pattern, and from the distortions in the interference pattern you can derive topography. And this, in fact, was done on the Earth in what was known as the Shuttle Radar Topography Mission a few years back, and that became the kind of default, generated high-resolution topography for most of the, well, for the latitude bands that the shuttle flies at, which does not cover Alaska, by the way, but or most of Alaska. But so there are different ways that you can use radar to get high resolution, to improve dramatically over what Magellan was able to collect. But yeah, but you do not have the option of using optical, LiDAR, or the laser altimeters work at optical, mostly optical wavelengths or near optical wavelengths, and so they won't penetrate through the clouds, so you can't use that option.
All right, well, we're getting on to about 45 minutes into this broadcast, so I think it's time to open things up for questions. Again, those of you who are watching this on Google+, I'm Emily Lochtawala from the Planetary Society with Robbie Herrick from the University of Alaska Fairbanks talking about Venus geology. And I hope you will +1 this broadcast on Google+, so we can see how many people of you are actually watching live. I know that a lot of you are probably watching this recorded, and we'd like to hear from you then, too. You can just post a comment on the YouTube video. But for those of you who are watching live, you now have an opportunity to ask questions. You can post those in the comments on Google+, or via Twitter using the hashtags #CQX, #Hangout, and I'll look for those and ask them of Robbie. I see one question so far from Samir Hariri, who wants to know about the age of Venus's surface. And he notices that the pictures of the craters, it makes it look very lava-like, as though there's lava right there. Can you talk about how old is the surface of Venus, and is there really lots of lava just lying around very close to the surface ready to erupt, or is it more like Earth?
Well, that is one of the debates that has come out of the Magellan mission. Overall, the surface of Venus is substantially younger than the other non-Earth terrestrial planets. So on the whole, the most of what we see on the surface is certainly less than 1 billion years, whereas if you look at the Moon or Mercury or Mars, you're looking at surfaces for the most part, certainly excluding what's going on Mars with some erosional, dust dunes and things like that. You're looking at surfaces that mostly are in the few billion year range. So Venus as a whole is much younger than those other planets, and its mean surface age, depending on who you talk to, is somewhere between tens of millions of years and a few 100 million years. And so for comparison, in terms of the Earth, all of the Earth's ocean basins have formed within the last couple 100 million years. So now how that is distributed in detail on Venus is a topic of debate. There are some people
you might say that. It's just a little bit debated in the Venus community.
So there are some people that have looked at so based on, and where this comes from on Venus, we don't have the ability to date the rocks on Venus remotely. So where this is coming from is all from the cratering record. So compared to, say, the Moon or Mercury, Venus is relatively crater-free. There are less than 1,000 impact craters on the surface of Venus, which is many times the surface area of the Moon.
It's pretty comparable to the number of craters on Earth, actually.
Right. Well, there's yes and no. I mean, there's a few hundred craters that have been discovered on Earth, but those are better described as impact structures. So when you're counting the number of craters on Earth, you're counting you're counting about 250 things that from an aerial photograph you could not really recognize as a crater, and you're counting about a dozen things that actually look like a typical impact crater with a raised rim and a hole in the ground and things like that. Whereas on Venus, the 1,000 craters, these are well enough preserved that you can clearly tell that they're an impact crater and they've got ejecta and things like that. Where the debate comes in is to there are two viewpoints as to some people think that all of these craters have more or less been unaltered since they formed. Work that I and some of my colleagues have done suggests that the majority of these have experienced at least some flooding by later lavas. And so
and the reason that this distinction is important is because if all the craters were unaltered since they formed, then that means that nothing geologically has happened to the surface since they formed. And so you basically had a clean slate of the whole planet, and then nothing's happened since that clean slate was made. And if that's true, then something happened to all of Venus 500 million years ago to erase everything and basically start over. Whereas if you are finding evidence that things have been modified since they formed, then that means that Venus has been geologically active more recently.
That's right. And so I tend to think that the latter has happened, that there's been a continuous, there's been a fair amount going on. Now, the interesting thing is from the Magellan mission, because of its relatively short duration of a couple of years and the resolution it had, we don't really have the ability to answer through direct examination as to whether volcanism is currently occurring on the surface.
It's probably a pretty good indicator if a debate has been going on for 20 years that there simply isn't the data necessary to solve the debate.
Right. So yeah, and so if we, even under the most pessimistic scenarios that people have, Venus almost certainly is still active volcanically, but whether that level of volcanism is a small fraction of Earth's level of volcanism or equal or maybe even exceeding Earth's level of volcanism is a matter of debate, and that's another thing that it would be nice to go back and have a mission that somehow is able to try and monitor and determine to some degree the level of current volcanic activity.
Yeah, one thing that's changed Mars geology a lot recently is the fact that we've had spacecraft in orbit there for so long. It's been well over a decade, and we've been able to see actual places on the surface of Mars change with time. Most of these changes are things like dry dust avalanches. You don't need very active geology for them to happen. But still, even the changes that we have noticed are so much more than anybody thought so much more activity on Mars than anybody really thought was happening before Mars Global Surveyor actually arrived. And we've never had a mission at Venus for long enough, or a series of missions at Venus long enough, that could actually detect changes, look for places that are pretty young volcanoes and see if there's any change in the pattern of if there's a new lava flow that forms over time. Like you can see at Io, for instance. You can see those, the mountains on Io are changing all the time because there's constant eruptions there, and you can actually track this lava flow between, September 79 and so on. And we can't do that for Venus. We just don't have the data, and that's another reason why we need another mission that can see beneath those clouds.
Right, and one thing to point out, almost all the changes that we've observed on Mars, these are changes that you can see in images that are, tens of meters across with a resolution of a meter or a few meters or less. And so all of these would be single pixels in the Magellan data. So even if we could go back now and recollect another day of Magellan, the resolution is still low enough that it would really be hard to do that. And we will actually have, because Arecibo is going to collect a map of Venus this summer and that will be data that's even worse resolution than Magellan, but like a 1 to 2 kilometer image. And so if there's some huge, enormous change, we'll be able to detect it because we have an image from Arecibo from 1980. And so, and they're going to collect it almost identical viewing geometry and conditions as then. So this summer there will be a new data set collected by Bruce Campbell and his colleagues at Arecibo, and they will in fact try and look and hope for some it would really be a big change if they detect something, but they'll have a chance to do that this summer.
That's cool, and I guess it's worth mentioning that Venus Express has been looking for things like glowing warm hot spots or strange puffs of new gas in the atmosphere, and so far has not found anything that's convincing to anybody. So that's a bit of a disappointment, I think, but they're still looking. They are there and they're looking. But we're getting pretty close to 5 o'clock my time, I guess 4 o'clock your time, and I think that probably that's the notion that it will at least have some kind of new data set coming this summer is a good place to stop. But it's also a good time, I think, to ask people to write their congressman and say that NASA needs more money in order that we can fly some more great missions, either orbiting Venus and looking down as you want to, or getting under the clouds and driving around. Man, do I want a rover on the surface of Venus. That would be so cool.
Right, yes. As a final comment, one of the challenges in getting below the clouds is having something last for a long time on the surface. And so some of the concepts that people have floated to, rather than having rovers, say, is to have something that's in a balloon and dips down for a couple of hours and looks at the surface and takes some pictures and then goes back up into the upper clouds. And so if you actually get about 30 kilometers up in the Venusian atmosphere, it's at about room temperature and
the clouds are at very high elevation, right? So even if you're that high, you're still very far from the surface, so you wouldn't have the resolution that you would have closer to the surface. But the clouds are still above you, I believe, at 30 kilometers.
Yes, I think that is true.
I think they're at like 50 kilometers.
That's true, but it's tough to know what the thermals would be like in terms of how they would distort images.
Right.
But yes, so that's. But anyway, so I'm not sure if a rover is feasible, but there are some other cool ideas people have floated in terms of landers and balloon things that you could explore the surface in ways that, of course, on Mars you can't. A balloon is much more. You have a lot less atmosphere to work with. So it would
work great on Titan, though.
Yeah. So. So there are a lot of other ideas out there for how to explore Venus, but it's all a matter of money and technology.
Right, as it always is. Venus may be a little bit more so than others, but that's no excuse for not going back. So on that note, I think I'll thank you, Robbie, for taking the time to both set this up and to sit through it and hour of conversation, tell us all about Venus. And this has been, I'm Emily Lakdawala for the Planetary Society, and thank you all, those of you who have been watching us converse about Venus geology. If you're still watching, please +1 this on Google Plus so we can know how many are watching live. And then if you're watching it recorded, please post a comment or a like or whatever it is. Actually, I forget what you do on YouTube now, to indicate that you watched and that you like it. So thanks very much for your attention. Thank you, Robbie, very much.
Oh, and thank you for hosting this, and it's my pleasure, and I'm always happy to talk of Venus to anyone who will listen. So thanks very much.
Excellent. All right, thank you, and hope to talk to you again.
All right, bye-bye.